When you stare up at the night sky, it looks peaceful and beautiful, a serene tapestry of twinkling lights against a velvet black canvas. But what if I told you the universe is not just beautiful, it's terrifying? That placid-looking expanse is a cosmic stage where dramas of unimaginable scale and violence unfold every single moment. Space is filled with forces so violent and phenomena so strange that they defy human logic, pushing the boundaries of what we thought was possible. These aren't the monsters under your bed. These are the monsters that the bed, the room, and the entire house. Imagine places where time itself stops, where the very fabric of space-time is torn asunder, where light can't escape the clutches of an insatiable gravity. Think of invisible forces shaping the destinies of entire galaxies, pushing them apart or holding them together with a grip we can't even see. And consider the chilling possibility that the universe we know, everything we are and ever will be, could one day simply disappear in the blink of a cosmic eye. These are not ideas from horror stories conjured by a writer's imagination. They are discoveries from modern science rooted in the mathematics of astrophysics and the observations of our most powerful telescopes. These concepts challenge our sense of security, our place in the cosmos. They force us to confront the sheer scale and indifference of the universe. What you're about to hear might make you feel small, but it will also, I hope, fill you with a profound sense of awe. If you haven't already, hit that subscribe button on beyondx and leave us a comment about which part of space terrifies you the most, because what you are about to hear might change how you see the universe forever. Let's get started. Let's begin with the classics, the undisputed heavyweight champions of cosmic terror, black holes. What are they? In simple terms, a black hole is a region of space-time where gravity is so strong that nothing, not even light, the fastest thing in the universe, can escape. It's the ultimate cosmic prison. They are born from the death of massive stars, stars many times more massive than our own sun. When such a star exhausts its nuclear fuel, its core collapses under its own immense gravity, crushing down into an infinitely dense point we call a singularity. This collapse warps space-time so severely that it creates a one-way door into oblivion, the event horizon. Think of it as a waterfall in the river of space. If you're a boat far upstream, you can paddle away, but once you cross the edge of the falls, the current is too strong. No amount of paddling, no engine can save you. You are going over. The event horizon is that point of no return. Once you cross it, all paths in your future lead to one place, the singularity at the center. The escape velocity at the event horizon is greater than the speed of light. Since nothing can travel faster than light, nothing can escape. This is why black holes are, well, black. They don't emit or reflect any light, making them invisible to the naked eye. We can only infer their presence by observing their effects on nearby matter, stars being whipped around an unseen center, or gas being heated to millions of degrees as it's pulled in, creating a brilliant accretion disk just outside the event horizon. And near this boundary, reality itself gets weird. Time, as Einstein taught us, is relative. For an observer watching from a safe distance, someone falling toward a black hole would appear to slow down, their image getting redder and dimmer until they seem to freeze at the event horizon, trapped for an eternity. But for the person falling in, time would pass normally. They would cross the event horizon in a finite amount of time, blissfully unaware of their frozen image left behind, on a one-way trip to, well, we don't know for sure. The journey inward is a process physicists poetically call spaghettification. The tidal forces, the difference in gravitational pull between your head and your feet, would become so extreme that they would stretch you out like a long thin noodle of human pasta. It's a gruesome end to be sure. For the longest time, black holes were purely theoretical constructs, mathematical oddities in Einstein's equations. We had strong indirect evidence, but we'd never won. That all changed in 2019. The Event Horizon Telescope, a global network of radio telescopes working in concert, gave humanity its first ever direct image of a black hole's shadow. There it was, in the galaxy Messier 87, 55 million light-years away, a dark central region surrounded by a glowing ring of superheated gas. It was a confirmation of one of the most terrifying and fascinating predictions of modern physics. We were staring into the abyss, and for the first time, we saw it staring back. Imagine our Earth, our home, not as a cozy world orbiting a life-giving star, but as a frozen, dark wanderer, hurtling alone through the interstellar void. This isn't just a science fiction nightmare, it's the reality for countless worlds known as rogue planets. These are planets that don't orbit a star. They are cosmic orphans, untethered and drifting through the vast empty spaces between star systems. How does a planet go rogue? It's a story of gravitational chaos. In the early turbulent days of a solar system's formation, planetary orbits are not always stable. The gravitational tug-of-war between multiple large planets can be intense. Sometimes a smaller planet gets too close to a gas giant, like Jupiter in our own system. The giant's immense gravity acts like a slingshot, flinging the smaller world out of the system entirely, ejecting it into interstellar space with such velocity that it can never return. It's a planetary eviction notice served with extreme prejudice. Once ejected, the planet's fate is a bleak one. Without a star to warm it, its surface temperature plummets to near absolute zero. Its atmosphere freezes solid, blanketing the surface in a thick layer of nitrogen and oxygen ice. Any oceans it once had would freeze to the core. Life as we know it, dependent on liquid water and stellar energy, would be extinguished almost instantly. The planet becomes a dark, frozen tomb, traveling silently through the galaxy for billions of years. So what would happen if our Earth became a rogue planet? The initial chaos of the ejection would cause catastrophic earthquakes and volcanic eruptions. But the real horror would begin once we left the sun's embrace. Within days, the average surface temperature would drop below freezing. Within a year, it would be 100 degrees below zero. The oceans would freeze over, creating a global ice sheet miles thick. Humanity's only hope for survival would be to retreat deep underground, harnessing geothermal energy from the planet's core. You might think such objects are rare, exotic exceptions, but you would be wrong. Astronomers now estimate that there could be billions, perhaps even trillions of rogue planets in our Milky Way galaxy alone. For every star you see in the night sky, there could be dozens of these dark, starless worlds drifting unseen in the darkness. They are an invisible population of cosmic ghosts, outnumbering the stars themselves. Every so often, one of these wanderers might pass through our solar system. A small one might go unnoticed. But a large one, a gas giant-sized rogue, could wreak havoc, its gravity disrupting the orbits of our planets, potentially sending a shower of asteroids toward Earth, or, in a worst-case scenario, destabilizing our own orbit. These silent travelers are a stark reminder that even in our seemingly stable corner of the cosmos, we are not entirely safe from the galaxy's hidden dangers. Of all the violent events in the universe, few can match the sheer, unadulterated power of a gamma-ray burst, or GRB. These are the most energetic and luminous electromagnetic events known to occur in the universe since the Big Bang. For a few brief seconds, a single GRB can outshine all the stars in the observable universe combined. It is, for all intents and purposes, a cosmic death ray of incomprehensible scale. Imagine the entire energy output of our sun over its 10 billion-year lifespan, released in a matter of seconds. That's a GRB. So what could possibly create such a cataclysm? We know of two main culprits. The first is the hypernova, the death of a truly massive star, many times larger than the ones that form standard supernovae. As its core collapses into a black hole, powerful jets of plasma are blasted out from its poles at nearly the speed of light. If one of these jets happens to be pointed directly at you, you see a gamma-ray burst. The other source is the collision of two neutron stars, the ultra-dense remnants of dead stars, spiraling into each other in a final, violent embrace. These bursts unleash a focused beam of high-energy gamma radiation. If you're in the path of this beam, you're in trouble. Even from thousands of light-years away, a GRB could have devastating consequences for a planet like Earth. The gamma rays themselves wouldn't reach the surface, our atmosphere would absorb them, but in doing so, the atmosphere itself would be cooked. The radiation would rip apart nitrogen and oxygen molecules, destroying our protective ozone layer. Without the ozone layer, the Earth would be blasted by deadly ultraviolet radiation from our own sun. This would trigger a mass extinction event, particularly affecting marine life like plankton, which form the base of the entire oceanic food chain. The chemical reactions in the upper atmosphere would also create a thick, reddish-brown smog of nitrogen dioxide, blocking out sunlight, plunging the planet into a sudden ice age, and causing acid rain to fall from the sky. Some scientists theorize that a GRB may have already been responsible for one of Earth's major mass extinctions, the Ordovician-Silurian extinction, about 450 million years ago. The fossil record from that time shows a pattern of extinction consistent with the effects of a nearby gamma-ray burst. We were lucky. The burst was likely far enough away that its effects were damaging but not completely sterilizing. The terrifying part is the randomness. These events happen without warning. We are constantly being bathed in the faint, distant afterglow of GRBs from faraway galaxies. But if one were to occur within our own Milky Way, say a few thousand light-years away, and its jet were pointed directly at us, there would be no defense. We would see a brilliant new star in the sky, and then, months later, the high-energy wave would arrive. It's a game of cosmic roulette, and we can only hope our number doesn't come up. Stars, like people, are born, live, and eventually die. But when a truly massive star dies, it doesn't go quietly. It goes out in a blaze of glory called a supernova, which is honestly an explosion so bright it can briefly outshine its entire host galaxy. This is, the universe's ultimate fireworks display, and it is both a creator and a destroyer. The process begins when a star at least 8 times the mass of our sun runs out of hydrogen fuel in its core. For millions of years, the star has been in this delicate balance between the outward push of nuclear fusion and the inward pull of gravity. But when the fuel runs out, fusion stops. Gravity wins. The core collapses catastrophically in less than a second, shrinking from the size of the Earth to a ball just a few miles across, forming an ultra-dense object called a neutron star. The outer layers of the star, now unsupported, come crashing down onto this new, incredibly hard core. They rebound in a titanic shockwave, blowing the star apart in a supernova explosion. This blast releases an incredible amount of energy and matter into space, and this is where the creative aspect comes in. The extreme temperatures and pressures in the explosion actually forge elements heavier than iron: gold, platinum, uranium. Every atom of gold in your jewelry, every atom of calcium in your bones that wasn't created in an earlier generation of stars was forged in the heart of a dying star and scattered across the galaxy by a supernova. We are, quite literally, made of stardust. But there's a more violent cousin to the supernova, the hypernova. These are the explosions I mentioned earlier, thought to be the source of long-duration gamma-ray bursts. They are at least 10 times more energetic than a typical supernova, and occur when stars more than 30 or 40 times the mass of the Sun die. Instead of leaving a neutron star, their core collapses all the way down to a black hole. Hypernovae are the true titans of stellar death. While they are essential for creating the elements necessary for life, you definitely do not want to be anywhere near one when it goes off. A supernova within about 50 light-years of Earth would be catastrophic. The initial blast of radiation, X-rays and gamma rays, would strip away our ozone layer, just like a GRB, exposing life on the surface to lethal solar and cosmic radiation. The long-term effects would be just as devastating, as a wave of high-energy cosmic rays would wash over our planet for centuries. And we have a prime candidate for such an event right in our cosmic backyard. The red supergiant star Betelgeuse in the constellation of Orion is in the final stages of its life. It's about 650 light-years away. Too far to cause a mass extinction, thankfully. But when it finally explodes, and it could be tomorrow or it could be 100,000 years from now, it will be an unforgettable spectacle. It will shine as brightly as the full moon, visible even during the day for weeks on end. It'll be a stunning and honestly humbling reminder of the power and violence that shapes our universe. So far, we've talked about things: black holes, rogue planets, exploding stars. They are tangible, if terrifying, objects. But this next horror is different. It's not a thing, but a change in the state of reality itself. It's a concept from quantum field theory called vacuum decay, and honestly, it might be the most existentially terrifying idea in all of physics. It suggests that our entire universe could be a ticking time bomb, living on borrowed time. To understand this, you need to think about the vacuum of space not as empty nothingness, but as a field, the Higgs field, that permeates all of reality. Like any physical system, this field wants to be in its lowest possible energy state, what we call the true vacuum. But what if it isn't? What if the universe is currently in a false vacuum, a state that is stable, but not the most stable state possible? Think of a ball resting in a small dip on the side of a large hill. It's stable for now, but not as stable as it would be at the bottom of the hill. The laws of quantum mechanics allow for something called quantum tunneling. This means there's a tiny but non-zero probability that our ball could spontaneously tunnel through the hump of the hill and start rolling down to the true, lower energy state. If this happened to the Higgs field, a bubble of true vacuum would spontaneously appear somewhere in the universe. Inside this bubble, the laws of physics as we know them might be completely different. The mass of elementary particles like electrons and quarks could change. The strengths of fundamental forces could be altered. The very structure of atoms could become impossible. This bubble of new physics, of true vacuum, would expand outward in all directions at the speed of light. And because it travels at the speed of light, we would have absolutely no warning of its arrival. You wouldn't see it coming. One moment everything is normal. The next moment you, the Earth, the Sun, the entire galaxy simply cease to exist in any recognizable form as the bubble wall washes over you, converting our false vacuum into the true vacuum. It's not an explosion, it's a phase transition. It's like a pot of boiling water suddenly turning into a block of ice with completely different properties. There would be no fanfare, no dramatic explosion, just an end. Is this going to happen? We have no idea. For all we know, our vacuum could already be the true vacuum and we're safe. Or, the energy barrier to the true vacuum could be so high that the time it would take for a bubble to form is trillions of times longer than the current age of the universe. But the fact that the equations allow for it, that our universe could be fundamentally unstable, is a chilling thought. It's the ultimate cosmic threat. The rules of reality itself could change without notice. Where is everybody? This simple question, famously asked by the physicist Enrico Fermi, lies at the heart of one of the most profound and unsettling mysteries in science, the Fermi Paradox. The paradox is this: our galaxy, the Milky Way, contains hundreds of billions of stars. Many of these stars are billions of years older than our Sun. It seems statistically probable that many of these stars should have Earth-like planets, and that on some of those planets, life should have evolved. If even a tiny fraction of those life forms developed intelligence and technology, the galaxy should be teeming with civilizations. Given the age of the galaxy, some of these civilizations would have had a head start of millions or even billions of years on us. With that amount of time, they should have been able to colonize the entire galaxy, or at the very least, leave some unmistakable sign of their existence: radio signals, giant alien megastructures, probes. Yet when we look and listen, we find nothing. The cosmos is eerily silent. This silence is the horror. It implies that something is wrong with our assumptions. Scientists have proposed many possible solutions to the paradox, and some of them are deeply disturbing. One is the idea of a great filter. This is some barrier or challenge that is so difficult to overcome that it prevents almost all life from reaching an advanced spacefaring stage. The filter could be behind us. Perhaps the jump from non-life to life is incredibly rare. Or more ominously, the great filter could be ahead of us. Maybe every advanced civilization eventually discovers a technology that leads to its own self-destruction, like nuclear war or runaway climate change or an out-of-control AI. In this scenario, the silence we hear is the silence of a cosmic graveyard filled with the ghosts of civilizations that failed to pass the test. We might be one of the first to reach this point, and the odds are stacked against us. Another chilling explanation is the dark forest hypothesis, inspired by a science fiction novel. In this scenario, the galaxy is like a dark forest filled with hidden hunters. Every civilization is a hunter, and their primary goal is survival. Because you can never know the true intentions of another civilization. Will they be friendly or hostile? The safest course of action is to remain silent and hidden. If you reveal your location, you risk being destroyed by a more powerful hunter who sees you as a potential threat. In this view, the silence isn't because no one is out there, it's because everyone is terrified, holding their breath and hoping not to be noticed. The first civilization to shout, "We are here," is like a lost child crying in the dark forest, alerting every predator to its presence. Our own radio and television broadcasts have been leaking into space for a century now. If the dark forest hypothesis is correct, we may have already made a fatal mistake. The silence, in this case, is not an absence of life but a presence of fear. When you look up at the night sky, all the stars, galaxies, planets, and nebula you can see, everything that gives off light, accounts for less than 5% of the total mass and energy in the universe. The other 95% is completely invisible to us. It is the dark side of the cosmos, composed of two mysterious substances we call dark matter and dark energy. This isn't just a small rounding error in our cosmic census. It means we are fundamentally ignorant about what most of the universe is actually made of. About 27% of the universe is thought to be dark matter. We can't see it, we can't touch it, it doesn't interact with light or any other form of electromagnetic radiation, so how do we know it's there? Gravity. We see its gravitational effects everywhere we look. We see galaxies spinning so fast that they should fly apart, but they don't. There must be a huge, invisible halo of extra mass providing the gravitational glue to hold them together. That's dark matter. We see light from distant galaxies being bent as it passes through galaxy clusters, an effect called gravitational lensing, and the amount of bending implies far more mass than we can see. Dark matter forms the invisible scaffolding upon which the visible universe is built. Galaxies form and cluster along vast, unseen filaments of dark matter. It is the silent gravitational puppeteer of the cosmos. The horror here is one of ignorance. We live in a universe dominated by a substance we cannot identify. Is it composed of exotic, undiscovered particles? Is our theory of gravity wrong? We simply don't know. We are like ancient mariners on a vast ocean, aware of deep currents moving our ship, but unable to see the water itself. If that weren't enough, the remaining 68% of the universe is even stranger. This is dark energy. In the late 1990s, astronomers made a shocking discovery. They expected to find that the expansion of the universe, which began with the Big Bang, was slowing down due to gravity. Instead, they found the exact opposite. The expansion is accelerating. Galaxies are flying away from each other at an ever-increasing rate. Something is pushing the universe apart, acting as a sort of anti-gravity. We call this mysterious force dark energy. We have even less of an idea what dark energy is than we do about dark matter. It appears to be a property of space itself. The more space there is, the more dark energy there is, which causes space to expand even faster, creating more space and more dark energy in a runaway feedback loop. This leads to a chilling potential fate for the universe known as the Big Rip. If dark energy continues to grow stronger, its repulsive force will eventually overcome all other forces. First, it will push galaxy clusters apart. Then it will overcome the gravity holding individual galaxies together, flinging the stars into the void. As the acceleration continues, it will become strong enough to rip solar systems apart, separating planets from their stars. In the final moments, it will overwhelm the electromagnetic forces holding atoms together, and finally, it will tear apart atomic nuclei themselves. The very fabric of space-time will be ripped to shreds. It would be the ultimate violent end to everything. If the universe avoids the fiery end of the Big Rip, it faces an alternative fate, one that is perhaps even more terrifying in its quiet, drawn-out finality, the heat death of the universe. This isn't a sudden cataclysm, but a slow, inexorable slide into darkness and cold. It is the ultimate consequence of the second law of thermodynamics, the principle that entropy, a measure of disorder or randomness, always increases in a closed system. And the universe is the ultimate closed system. The story begins trillions of years from now. The accelerating expansion driven by dark energy has pushed all galaxies beyond our local group over the cosmic horizon. The night sky will be almost completely dark, save for the faint, dying embers of the stars in our own merged galaxy, Milkomeda. Star formation will have long since ceased, as all the free gas and dust will have been used up. The universe will be populated by the stellar remnants, white dwarfs, neutron stars, and black holes. Over unimaginable timescales, trillions upon trillions of years, even these remnants will fade. The white dwarfs will cool down to become black dwarfs, cold, dead spheres of carbon and oxygen invisible in the darkness. The planets will be stripped from their orbits by gravitational encounters. The remaining matter in the universe, through a process called proton decay, if it occurs, will slowly dissolve into a thin soup of photons and leptons. The universe will become a vast, cold, dilute, and featureless void. The only things left will be the black holes, and even they are not eternal. Thanks to a quantum process known as Hawking radiation, black holes slowly evaporate over truly mind-boggling timescales. A stellar mass black hole will take around 10 to the power of 67 years to disappear. The supermassive black holes at the centers of galaxies will last much longer, perhaps 10 to the power of 100 years, a number so large it's meaningless to the human mind. But eventually, even the last, most massive black hole will radiate away its final bit of mass and disappear in a final, faint pop of low-energy photons. At this point, the universe will have reached a state of maximum entropy. It will be a near-perfect vacuum, filled only with a diffuse, homogeneous bath of photons and other fundamental particles, all at a temperature infinitesimally close to absolute zero. There will be no more change, no more work can be done, no energy can be extracted, all motion will cease, time itself will lose its meaning as there will be no events to mark its passage. This is the heat death. Not a bang, not a rip, but an eternal, silent and unchanging darkness. It is the end of complexity, the end of structure, the end of information, the end of life, and the end of the story. The universe will simply be forever. So there you have it. Black holes that trap light rogue planets wandering in the dark cosmic death rays, and the slow, inevitable decay of reality itself. The universe, in its grandeur, holds terrors that dwarf any fiction we could invent. These concepts are not meant to make you lose sleep at night, well, maybe a little. They are meant to expand your perspective, to instill a sense of awe at the sheer scale and power of the cosmos we inhabit. Understanding these cosmic horrors doesn't diminish the beauty of the night sky, it adds a layer of profound, humbling context. We are living in a remarkable, fleeting moment in the universe's history, a time when the sky is filled with galaxies, when stars are being born, and when a species on one small planet is just beginning to piece together the cosmic story. The silence of the Fermi Paradox, the mystery of dark matter, the threat of vacuum decay. These are the great questions of our time. They are the frontiers of our knowledge, and pushing against them is what drives science forward. Every new discovery, every image from a telescope is a candle lit against the immense darkness. Thank you for joining us on this journey into the deepest fears of the universe. Our exploration of these cosmic horrors reminds us of how precious and precarious our existence truly is. It's a call to cherish our world and each other. If you enjoyed this exploration, please like this video, subscribe to beyondx, and share your thoughts in the comments, because together we will keep unraveling the mysteries of existence. Keep looking up.